Hi everyone. In this video, we're going to be looking a little bit behind the scenes and figuring out why that power rule works. And one thing I want to emphasize here is that this video lesson is not something that you need to memorize. I'm only making this video in response to, student curiosity about, we give you this power rule for evaluating derivatives of polynomials. And, to some of you, maybe it feels like magic, and if you want to sort of see, peek behind the curtain at why this works, this would be the video for you. But you might notice that this is going to be a more technical video than in the rest of the course, and if it seems like it's going over your head, I just don't want you to panic, right? So maybe just view it and gain an appreciation for why the power rule works. But again, do not feel stressed out and don't feel like you have to memorize anything going on here in this video. Now, in the previous lesson, one of the derivative rules we learned was called the power rule. And here I have stated the power rule, basically as we learned it. And just as an example of the application here, is that if I have the function x to the power 5, the derivative of that function would be 5 times x to the power 4. So the exponent decreases by 1, and again, the old exponent comes out in front and becomes a coefficient. And so again, in this video, we're going to explore why is this the case. I'm going to offer what we call a proof by induction, and we're going to start here just by proving the case of this power rule where we let n equal to 1. So what I'm saying is when you look at this power rule here in the blue box, if I set n equal to 1, why is that the case, right? We're going to ask the question, using the power rule, what would we expect to find for our derivative? So if I just rewrite the power rule again, and I just let this be x to the power 1, I expect my derivative to be 1 times x to the power 1 minus 1. So all I've done is I went back here and replaced all of the n's with 1's. So 1 minus 1 is 0, so we're talking about 1 times x to the power 0. X to the power 0 is just 1. So anything, whatever x is, anything to the power 0 is just the number 1, and 1 times 1 is 1. So if I let n equal 1, what I expect to find for my derivative is just the constant number 1. Now let's go ahead and we're going to remember what we stated for the definition of the derivative that came up in a few lessons ago. And so it's this limit as h approaches 0, and in the numerator we have our function evaluated at x plus h minus the function evaluated at the point x, all divided by h. And we are going to let our function, this time, that f of x function, that's going to be x to the first power. And so in other words, we're talking about the case where the power rule applies and n is equal to 1. And if we do this, what we're going to get for our derivative is to say the limit as h approaches 0 of, now our f of x plus h, when my f of x function is just x to the power 1, that's going to be x plus h to the power 1. And of course, the power 1, you can rewrite this without the power, and that also works. And heck, you could even rewrite it without the parentheses. So like this, just x plus h. So then, where I consider the function f of x plus h, I'm just going to write x plus h. And then whenever I subtract minus f of x, that's going to be minus x to the 1 power, or we might just write minus x, again divided by h. Now, here, if I see in the numerator, I have x, a positive x here, and then minus x, so x minus x. That's going to cancel each other out, and we're talking about then the limit of this ratio h over h. Now, whatever the value of h is, h divided by itself, that's just the number 1. And so we can simplify this limit even further and say that this is just the limit as h approaches 0 of the number 1. And the limit of a constant, I don't see any h's appear in my simplified version of this limit. And so I can just say, well, that limit must be the constant number 1. So what I found using the very definition of the derivative is that when I consider the function x to the power 1, in other words, I'm looking at the derivative power rule when n is equal to 1, what I get is 1, and that's actually nice to know because what we expected to find when we used the derivative power rule was that this derivative should also be just the number 1. And so far it checks out. So far, just for the case when n is equal to 1, our derivative power rule holds. It works properly like it should. It's actually giving us the derivative, and it hasn't failed us yet. So we have proved that this power rule works when n is equal to 1. And here we are at this point. And to continue, I just need to prove this statement. If the power rule works for n is equal to k, then the power rule also works for n is equal to k plus 1. And I invite you to pause the video and see if you can appreciate why this statement would be sufficient to prove the power rule for any number n, right? So like 1, 2, 3, 4, 5, any of the natural numbers. And to spoil it for you now, the reason it works is because the statement says if the power rule works for n equals 1, then it also works for n is equal to 2, right? This would be n is equal to 1 plus 1, so n equals to 2. And we could repeat the statement and say, well, if the power rule works for n is equal to 2, then it also must work for n is equal to 3. And if the power rule works for n is equal to 3, then it also must work for n is equal to 4. So actually for every natural number up to infinity, we can prove that the power rule will work for any natural number n if we can just prove this statement. And so I want to emphasize, we have yet to prove this, but this is our goal. This is what I want to be able to do so that I can say that we've proved the power rule in general. And so we're going to do this. And we're going to do this by first assuming that the power rule does work for some n is equal to k. And then we're going to prove that based on that assumption, the power rule also works for n is equal to k plus 1. And so we're also going to start from the definition of the derivative, starting from the very basics. And this time, we're going to choose a new function. We're going to say f of x is equal to x to the power k plus 1. And we're going to see that the power rule holds for this function, where this is basically saying that our lowercase n is equal to k plus 1. All right, so if we can do this, then we have proved what we have started out seeking to prove. So here we go. Let's do some algebra. We're going to write the limit as h approaches 0 of, and if this is my function f of x, then my function f of x plus h as an input, that's going to be x plus h to the power k plus 1. And that's useful here in your definition of the derivative. So starting off in the numerator, I have x plus h to the power k plus 1. And then I have minus f of x, so I'll do minus x to the power k plus 1. And then, of course, divided by h in my denominator. Okay, so let me write out the limit again, and we'll make some initial simplifications here. Whenever I have the exponent k plus 1, what I can do is pull out an x plus h and then multiply that times x plus h to the power k. Right? So whenever I make that multiplication, it'll make the exponent k plus 1. And I'll do the same thing with x. And so I'll rewrite this as x times x to the power k. And hopefully you can see why x times x to the power k would be the same thing as x to the power k plus 1. Okay, now the next thing I'll do is over here on the left side of my numerator, I'm going to kind of distribute this factor x plus h to the power k to each of these terms x and h in the preceding factor. And it'll make more sense when I write it out. So I'm going to set this equal to the limit again of x times x plus h to the power k plus h times x plus h to the power k. And then again, minus x times x to the power k, all divided by h. So far, so good, right? We're going to continue on the next row here. And I'll say that this, what we had before, is going to be equal to limit as h approaches 0. And I'm just going to rearrange the terms in my numerator to make my next step look more convincing, right? So I'm actually not going to be doing any particular math operations here. I'm just going to rearrange those terms in my numerator. So I have x times x plus h to the power k, and then I'll put the third term now second, so minus x times x to the power k, and then plus h times x plus h to the power k. So you notice no math happening in this step, just some rearranging of my numerator. Now, I'm going to factor out an x because I have a common factor x in the first two terms of my numerator. And that's all that's going to be going on here. So I have x times x plus h to the power k minus x to the power k. So you can see how I factored out that x from the first two terms. And then my third term is still hanging out by itself. I have h times x plus h to the power k divided by h. Awesome. And while I'm stuck here and maybe a little bit concerned about running out of room on my page, I want to point out that in the numerator here where you see this plus sign, I can actually break apart this fraction into two separate fractions. I just have to keep my denominator the same for those two fractions, right? And so let me do that. And I'm going to redraw this as two different fractions, both with the denominator h. And hopefully you've seen that before in algebra, and we understand why we can do this. I'm trying to take as few breaks as possible, because I know this is already going to be long. And then, after I make this step, and maybe some of you can already see, that I'm going to be able to cancel this h in the numerator with the h in the denominator, so those factors cancel. All right, now let's see where we're at after I make that cancellation. I'm going to rewrite this as the limit as h approaches 0. I'm going to let this x factor in my numerator of my first fraction inside the limit be out to the side, kind of, times, and then my new numerator of that first fraction will be x plus h to the power k minus x to the power k divided by h. Then I have plus x plus h to the power k. And I want to point out a rule of limits, actually two rules of limits in this particular step that we've talked about in a previous lesson. The first is that if you see terms added inside a limit, like where this plus sign is, I can actually break up my limit into two different limits at this plus sign, and so that's what I'll be doing. And also, where you see this multiplication going on, I can break up a limit into the product of two different limits at the multiplication sign. I'm going to be doing these kind of simultaneously so that this limit is now going to become three different limits. So I'll have the limit as h approaches 0 of just x times the limit as h approaches 0 of this x plus h to the power k minus x to the power k over h. And then again, plus, then I get my third limit where I broke it up the second time, the limit as h approaches 0 of just x plus h to the power k. And I'm starting to run out of space, but we're also getting so close to the end of the video. So this first limit, when I take limit as h approaches 0 of just x, notice I don't even have any h's, and so this limit here just becomes x. Now the third limit, I will maybe change my focus and focus on this part right here. The limit as h approaches 0 of this little bit, well, I actually can just substitute 0 in for h, so I'll let h actually become 0. And because this little bit right here, this expression, is continuous at that point, I just find that this limit evaluates to x to the power k, or x plus 0 to the power k, right? Same thing. So I'm adding that last limit. And so what I'm left with that I need to evaluate here is this bit in the middle. And the very astute among you would say, hey, this little bit over here that I've underlined in maroon, that is actually talking about the derivative of x to the power k, right? So maybe you recognize the definition of the derivative hiding in this limit here. And you say that's just the derivative of x to the power k. And I wouldn't blame you if you had forgotten this already, but we have made an assumption about the derivative of x to the power k. We assumed that the power rule works for when n is equal to k. And so using the power rule here, for x to the power k, my power rule tells me that that this derivative is k times x to the power k minus 1. And so I'm allowed to use this particular derivative because I made it an assumption. It's what we mathematicians call the induction hypothesis. So what I'll do is I'm going to replace that limit, the one that looks like the definition of the derivative for x to the power k, I'm replacing this with k times x to the power k minus 1. So now it's very colorful, and we're, again, very close to the end of the video. This is, just rearranging a bit. I have k times x to the power k minus 1 plus x to the power k. So x times x to the power k minus 1, that is just x to the power k. And if I add an additional x to the power k, this is like saying k plus 1 times x to the power k. Now, again, I wouldn't blame you if you had forgotten because this has already been 20 minutes. But what we were originally trying to find here was the derivative of x to the power k plus 1. We started off using the definition of the derivative to find the derivative of x to the power k plus 1. So what we found here is the derivative of x to the power k plus 1 is equal to k plus 1 times x to the power k. And you'll notice that this is exactly what the power rule would say for the case when n is equal to k plus 1. So we've confirmed that the power rule works for the case when n is equal to k plus 1, just so long as we can assume that it works for whenever n is equal to k. Okay? But that is exactly what I told you we were trying to prove. I said I just need to prove this statement. If the power rule works for n is equal to k, then the power rule also works for n is equal to k plus 1. And in this video, we have successfully proved that. And like I explained earlier, because we know it works for n is equal to 1, and we know that this statement is now true, this one is totally verified, this n equals 1 success implies the success of the power rule for n is equal to 2. And that then implies the success of the power rule for n is equal to 3, which implies the success of the power rule for n is equal to 4. And you can see how this goes on for every natural number we can plug in. So this is just, rock solid proof that our power rule that we introduced in the last video works for every natural number n. Alright, so kudos to you if you stuck around to the end of the video, and hopefully this satisfies your sort of curiosity about, how do we know? How do we even know that the power rule works? So I'll see you in the next video.